We'd like to present for you today some highlights in the cold forming of metal parts from wire. Cold heading used to mean bolts and nuts, and that's about all. Now it means parts, production of an endless variety of parts, because more and more of the metal components in our complex and growing economy are being engineered, you might say imagineered, for production from wire. Automotive parts like ball studs, truck wheel nuts, distributor cap inserts, commutator bars, spark plug bodies, piston pins, tappet bodies, and plungers. Other jobs like bowls, rollers, and races for bearings, electrical parts of many kinds, rollers, pins, and rivets for chains, faucet stems, gear blanks, hose couplings, bicycle parts, intake valves, and countless others. But let's start at the beginning. A rivet is one of the simplest cold-headed parts. Wire feeds into the header, is cut off and carried over to the die. The ram advances, and between the heading tool and the die, you form the head. In the 1/16" header, for example, this single-blow operation produces 500 rivets per minute. Tooling is simple and inexpensive, and quite a few parts are being made this way. The metal can be made to flow into almost any shape within plastic limits of the material. This brings us to the first rule of forging die design. Using low-carbon steels, you can upset a length equal to about 2½ diameters in one blow. To form larger heads, we use a double-stroke machine. This also has only one die, but two heading tools are mounted on an oscillating tool holder. The first tool forms a cone-shaped upset. The second tool forms the head. With this double-blow method, the head volume can be increased up to 4½ diameters. As the part becomes more complicated, we resort to variations. Some parts are formed in the die, some in the punch, while some are a combination. By taking 1,000 pictures per second, we can observe the forming of a carriage bolt. The cone blow gathers the stock and starts the metal flowing in the proper direction. The finish blow has a simple concave punch. The die shape forms the square under the head. The machine is a 5/16 double-stroke solid die cold header running at 175 pieces per minute. The hex washer head cap screw is an example of forming in the punch. Here we see a simple die and a more complicated heading tool. Forming this part requires a special knockout in the finish punch. The machine you see here is also a 5/16 double-stroke solid die cold header, producing 175 per minute. Flathead countersunk sheet metal screws are made at 175 per minute on a 5/16 cold header. The sliding cone tool supports the length of blank used for upsetting. This is an example of forming in the die by displacing with the punch. The sheet metal screw is die pointed to facilitate roll threading. This unusual rivet insert is made on a 3/16 header at 200 per minute. The cone is upset off-center. The part is completely contained in the die. This chainsaw rivet pin is made from 52/100 steel wire at 225 per minute. The die is carbide and heading tools are high-speed steel. The pin is held to extreme tolerances. Collar diameter plus or minus 5/10,000ths of an inch. Shank plus or minus 1,000. Cold forming this part has saved 47% in material alone. The machine has a solid cutter and knockouts in the cone and finish punches. Commutator bars are made on a 1/4 inch cold header, 2 at a time, at 240 per minute. Preformed copper wire, wedge-shaped, feeds in 2 strands at a time. 2 of these headers save one manufacturer more than $30,000 a month in material alone. A special cutter shears and transfers the blanks to the die. The dovetail shape is formed first in the die by the kick-out pin and the other end by the finish punch. The punches each produce up to 485,000 parts, while the die produces 5.5 million. This commutator bar and the chainsaw rivet pin are examples of cold header versatility in producing wasteless parts. The demand for higher production brings on the high-speed cold header. Years of research and development work enable these headers to combine endurance at sustained high speeds with the production of accurate metal parts from wire. These proven headers run at the highest safe speeds ever achieved. Button-head screw blanks, clean and perfectly central, are being headed here on a 1/8 high-speed header at 450 per minute. Observe the firm and steady transfer of the cut-off blank to the die. And finally, we form blanks and roll threads in one machine. This one-die, two-blow fastener maker produces completed parts. Threads are rolled, the ultimate in thread forming. Roll threading does not remove metal, but forms threads of highest quality. These number 6 button-head machine screws run at 400 pieces per minute. Hex washer head cap screws are threaded here at 175 per minute on a 5/16 machine. Another example of roll threading up to the head. We roll thread here flathead countersunk sheet metal screws at 175 per minute. Roll pointing forms the threaded point needed on sheet metal and wood screws. Carriage bolts, 175 per minute in the same machine that formed them from wire. Threads are rolled right up to the square under the head. Of course, when parts become still more complex, they are formed in more than one die. At this point, enter the multiple die headers. This 3/4 by 7 hex head cap screw is produced on a 3/4 4-die bolt maker at 50 per minute. The bolt maker performs 7 operations at once and produces a finished cap screw with every stroke of the machine. Since the introduction of the bolt maker in the 1930s, it has been built in 3-die, long stroke, socket head, and 4-die designs. It produces square and hex head bolts, socket head cap screws, and many special parts, all automatically from coiled wire. As the wire feeds in, it is cut off and transferred to successive forming dies. In the first die, the blank is extruded to the body size of the bolt. In the second die, we form a round head. In the third die, another extrusion for the threaded section. And in the fourth die, the round head is trimmed to the hexagon shape. As the head is trimmed, the bolt is kicked back through the trim die and pushed up a tube to the pointer. A bolt needs a point to ensure easy starting. It's guided into the pointer station, gripped, and pushed down into the spinning cutters, which cut a bevel on the end. From here it pushes up a track to the roll thread station. Roll threading produces smooth, strong, quality threads. With every stroke of the machine, you get a completed part. This steering knuckle ball stud is produced on a 3/4 3-die bolt maker from 8640 steel wire at 50 studs per minute. You need 3 dies to gather stock and form the part. In the last punch, the long pin supports the heavy ball until the picker is in control of the blank. The picker transfers the part from the final station to the pointer tube entrance. A timed air blast blows the part up the pointer tube. The parts leave the machine after pointing. The end is threaded after a grinding operation. This ball stud is produced on a 5/8 4-die bolt maker from 1038 steel wire at 60 per minute. The tapered shank and the sharp corner made this a challenging forming job. Following cutoff, the part is formed in 3 dies. It is blown up the pointer tube in the 5th station. An air-operated pointer chuck keeps the round-headed part from spinning with the cutters. Because of the unique shape of the head, we move the part up the tracks with a conveyor. Threads are rolled on the small end up to the shoulder. This purlin roof fastener is made on a 5/16 4-die bolt maker from 1015 steel wire at 90 per minute. The part has radical extrusions on both ends and a collar upset in the middle. In the first station, the wire is cut to length. In the second, the small end is extruded in the die. In the third, a cone is formed and the large end extruded in the punch. In the fourth, the collar is upset, and in the fifth, the blank is blown up the pointer tube. Special knockouts are in the second and third punches. As before, the air pointer chuck grips another unusual shape of head during pointing. From the pointer, the parts are pushed up the track to the roll thread station. The small end is threaded to the shoulder. Some parts do not require pointing or threading, like this starter solenoid contact made on a 1/2-inch 4-die progressive header from pure copper wire at 90 per minute. A progressive header is basically the same as a bolt maker, but without pointer or roll threader. In 3 dies, the wire is upset from 5/8 of an inch to 1 1/4 inches. Prior to cold forming, these parts were stamped from copper sheets with over 32% scrap. By cold forming, scrap loss is only 12%. In the last station, the center is punched out and the slug is discharged through the bottom of the punch holder. The transistor base is made on a 1/2-inch 4-die progressive header from copper wire at 70 per minute. The small shank is extruded from the copper slug. In the first 2 dies, a 1/8 shank and a 1 1/8 inch body are formed from 1/2-inch wire. The second and third dies have spring-loaded blank supports to hold the part until the fingers close on the small shank. In the last die, the part is trimmed with only 2/3 of 1% scrap. This machine has special kick-out cams for short kick and special transfer parts. This truck wheel nut is made on a 3/4 3-die progressive header from 1018 steel wire at 50 nuts per minute. This is an example of extruding a hollow part. In the first die, the blank is dimpled. In the second, the flange is formed, and in the third, the extrusion forms the hole in the square end. This part was originally made by machining an 18-ounce blank. Cold forming needs only 6 ounces of stock. After the extrusion, the part is carried back on the punch. A stripping mechanism removes the part. To complete the nut, it is threaded inside and out. Now let's look at cold nut forming. Most of the metal from the hole is retained in the body of the nut. Here, a 3/4 inch hexagon washer face nut is formed at 60 per minute on a 3/4 cold nut former. Notice how we transfer the nut from die to die. In 5 operations, the cutoff blank is squared, formed, and the center punched out. The rotating transfer turns the blank 180 degrees between each die. This allows working on both sides, improving the mechanical properties of the nut. Cold forming produces nuts with smooth surfaces and very close dimensions. Machines are built in sizes from 1 inch down to 1/4 inch, at production rates from 40 to 140 pieces per minute. Scrap loss is only 5 to 15%, depending on the type of nut. In the last die, the center is punched out and the nut is carried back on the punch. A stripper clears the punch for the next blow. This 70-amp electrical connector is produced on a 3/8 cold former at 100 pieces per minute. The only scrap is the small slug at the right, a rectangular shaped part from round wire, both copper and aluminum. A cold former is a special cold nut former arranged to make odd-shaped parts. This includes changes on the transfer, special cutoff, or kickouts in the punches. Prior to the development of this connector on a cold former, you had to machine and drill these parts. The round wire is first cut off and the blank squared. Then the hole is extruded and the squared body formed. When the long projection is extruded, a sliding die forms a closed cavity for the metal to flow into. The transfer rotates the blank 180 degrees in the first two stations only and carries straight across in the last two. In the last operation, the hole is punched. The slug is punched back and out the bottom of the punch holder. Scrap is only 5%. Spark plug bodies are formed on a 5/8 cold former from 10-12 steel wire at 60 per minute. Almost all of the metal from the hole stays in the shell. An intensive development program ended successfully with the production of more than 125,000 parts on our own test floor. The proving of this part on the cold former has started quite a trend in cold forming spark plug bodies. Some of the requirements of this job are to maintain a thin wall on the skirt, fill the hex, high reduction of area in the extrusion, a tapered hole, achieve proper hole configuration, and yet maintain practical tool design. The blank transfers straight across in all stations. In the final operation, the small slug is punched from the hole. The part is carried back on the punch and stripped off. In the third and fourth punches, knockouts keep the part from pulling out of the die on the punch. The die lubricant and coolant is a special extrusion oil. Pins projecting from the last die push the punch-out sleeve away from the punch when the machine is running without work. The only secondary operations required to finish this plug are to turn the end on top of the hex, roll lettering and knurling on the body, and roll thread the end. Different gauging operations indicate the extreme accuracy to which these parts are now routinely made. Taper inside hole, plus or minus 1/4 degree. Inside length of shank, plus 5/1000 minus nothing. Small hole inside diameter, 7/1000. Large hole inside diameter, 5/1000. Body length, plus or minus 5/1000. Shank length outside, plus or minus 2/1000. Concentricity between large and small inside diameter. Shank end outside diameter, 2/1000. Body outside diameter, 10/1000. Skirt outside diameter, plus 10/1000 minus nothing. In cold forming, the metal fibers are rearranged to follow the contour of the part. This ensures maximum strength. And finally, the latest in automatic cold forging machinery, a number 1000 7-station 6-die cold former, capable of great versatility and flexibility in producing unusual parts formerly considered impossible. Automotive piston pins are produced from 1019 coiled wire at 50 per minute. Starting with 1-inch diameter wire, this 6-die machine produces a part so perfect that grinding the outside is the only machining necessary. There is only 3.5% waste in the small slug punched from the center. The pin is held to very close tolerances. The concentricity is held to 5/1000 total indicator reading, and the length plus or minus 5 thousandths. The close tolerance on the length of the pin is possible because of the accurate cutoff. The die lubricant and coolant is a special extrusion oil. In the first two dies, both ends are marked for extrusion and a radius is formed on the inside and outside diameters. The blank is rotated 180 degrees between these two operations. In the third, one end is extruded in the die over an extrusion pin. In the fourth die, the other end is extruded over the punch. In the fifth, the center is punched out. The final operation coins the sharp edges caused by the punch-out. All corners are rounded, eliminating flaking during heat treating. The machine features a special cutoff, knockouts in 2 punches, and a finger opening mechanism in the last station. These 6-die machines have opened the door to creative cold forming. The need for variety is leading not only to more forming stations, but to the forming of parts in larger and larger sizes of more and more unique shapes. These cap screws are produced on the 1¼ bolt maker at 38 per minute. High-quality cap screws produced in large sizes come automatically from coiled rod. An 1¼ by 10 cap screw weighs almost 4 pounds. This largest bolt maker consumes a ton of steel and produces 494 cap screws every 13 minutes. The machine weighs more than 400,000 pounds and is powered by a 200 horsepower motor. The unit in the foreground is a wire drawer. This is automatic non-stop operation. Coiled hot rolled rod, pickled and limed, is fed into the wire drawer. The drawer reduces the diameter to 1 7/16 inches, an 82 thousandths reduction, and feeds the proper length into the bolt maker. A blank 10 inches long is extruded, headed, and trimmed in 3 dies. The transfer fingers are operated by cam-controlled air cylinders. Each set is individually adjustable. The stock gauge is motor-driven. Maximum length of bolt under the head is 10 inches, the minimum 2½ inches. Before the 1¼ bolt maker, cap screws of this size were produced on hot upsetting machines, usually by hand. By cold forming in the bolt makers, no further machining is required. The fatigue life of large cap screws, cold forged with rolled threads, is twice that of parts made by other methods. Tensile strength is 12.5% greater. After threading, the cap screw goes through a bolt washer. The conveyor carries the bolt through a spray of kerosene and detergent, which leaves the parts perfectly clean. We have just seen a 4-pound cap screw forged automatically on the 1¼ bolt maker. Could this 6-pound stem pinion be cold forged on a machine of this type? Here we see this pinion cold forged experimentally on a 3,000-ton maxi press. The 8620 steel bar is 1 7/8 inches in diameter and 8½ inches long. A phosphate and soap coating serves as the lubricant. The first operation is an extrusion requiring 92 tons. In the second blow, a cone and another extrusion take 112 tons. The final heading blow takes 2,000 tons of forging pressure. A still larger pinion was tested on this 3,000-ton maxi press. It was made from a bar 2 3/4 inches longer and 2½ pounds heavier. This 8 3/4 pound pinion required 3,190 tons of forging pressure. These tests were conducted to determine the tonnage necessary to cold forge a part of this size. One day, perhaps, this pinion and many other large parts will be cold forged automatically. Experiments like this lay the groundwork for the machinery and methods of tomorrow. In still another area of cold forging's ever-changing frontier, we see the seamless aluminum can. It could be a case, a cover, or any hollow component. This 11-ounce seamless aluminum beer can is made at rates up to 240 per minute on a 400-ton horizontal extrusion maxi press. Accuracy of product comes from two factors. The first is this rugged 52,000-pound cast steel bed frame designed to absorb fully the shock of impact extrusion. The second factor is the preloaded roller bearings, which give the heading slide maximum alignment. This top view shows the vibratory hopper feeding the blanks into the die area. The commercially pure aluminum blanks are 1/8 inch thick and 2.5 inches in diameter. In operation, the blanks are fed across in front of the die, where the punch carries them into the die for the backward extrusion. When the punch retracts, the cans are automatically stripped from the punch. With the magic of the high-speed camera, we can see the metal flow back around the punch. The cans have a wall thickness of 13 thousandths of an inch, plus nothing minus 1 thousandth, and a bottom thickness of 25 thousandths of an inch, plus or minus 5. The cans have a diameter of 2 7/16 inches and an untrimmed height of 5 inches. This 11-ounce can requires 250 tons to form. The die impression is only a 1/2 inch deep, deep enough to control the direction of metal flow around the punch. The oriented cans fall into the rubberized cradle of the conveyor. They are carried dent-free from the machine, ready for trimming, flanging, cleaning, filling, closing, and decorating. The rush to cold forging from wire is on. But why? Because the product is stronger than the material you start with. The plastic flow lines, the fibers, follow the contour of the part. Production is unbelievably high from small, compact machines. Cold forming saves a lot of metal. Many parts are made wasteless and ready to use. You get a smooth, bright finish, eliminating secondary operations. Jobs need not be concentric or symmetrical. Offset parts, squares and flats have become practical and profitable. Creative, ingenious die design becomes routine as parts-making people move metal into desired shapes instead of removing it. Developing better ways of making present products, getting in shape to produce the exciting new jobs, making them faster, stronger, and at lower cost than anyone ever thought possible. This is imagineering, but what you have seen here is only part of the story. There is so much more we'd like to tell you about these remarkable machines and modern cold heading methods. We invite you to make our plant your laboratory. Come to Tiffin with your jobs, your questions, and problems. Let's make a thorough study and determine how many of the parts you make should be made from wire.